In this video I'm going through an example of the geometric distribution. You use the geometric distribution if something's happening repeatedly with a constant probability of success, and you're trying to find the probability you get a success for the first time on the, what could be the 8th attempt or the 5th attempt or something like that. So we're looking here at an archer who's firing arrows at a target, and he knows there's an 80% chance that he hits the target on any attempt. He never gets any better, never gets any worse, it's always a constant 80%. For the geometric distribution there's one key value, and that's P, your probability of success, which is a decimal here, will be 0.8. So what I want to work out first of all is the probability he'll hit the target on the 3rd attempt, and that's their first time they've hit it. So the probability they hit the target on the first time, well, I'm going to say that's x equals 3. But before I do that, really I ought to say what x is. Well, x is going to be the attempt at which the first success occurs. So it's the attempt at which the archer first hits the target. So I want, if x is 3, what I want to know is what's the probability he or she hits the target for the first time on the 3rd throw. The formula for the geometric distribution is 1 minus p to the r minus 1 times by p. That's the formula here. P is the probability of success, and r is the number in here. So r is the attempt on which the first success happens. So if you think about this, 1 minus p, that's the probability of failure. So this is failing, well in this example, 2 times and then succeeding, which is what we want. So over here the calculation I need to do is 1 minus p to the power of 3 minus 1 times by p, which is 0.2 to the power of 2 times by 0.8. If I work that out, I get 0.032. If I wanted to find out what's the probability the archer misses on the first 9 times and gets the first success on their 10th attempt, then that should be quite low, with 80% chance of hitting it each time. X is 10 means it misses the first 9 times. That's going to be quite unlikely. So using the formula over here, it's 1 minus p, which is 1 minus 0.8, to the r minus 1, this is the r number here, so it's 10 minus 1, which is 9, times by p, which is that final success. So it's 9 failures and then a success. And if you work that out, you do get a very small number. In fact, you get a number that is so small it probably appears in standard form on your calculator as 4.096 times 10 to the power of minus 7, which means that 4 is the 7th digit after the decimal point. So a long number, very, very small, as expected. If I wanted to work out the probability that the first success is before his 5th attempt, I can show that by x is less than 5. That means the first success is on attempt less than 5. So it's either on the 1st, 2nd, 3rd or 4th attempt. So it's either on the 1st attempt, 2nd attempt, 3rd attempt or 4th attempt. If he's successful on the 1st attempt, that's just a 0.8 he hits it the first time. 2nd attempt is that 1 minus p to this number minus 1 times by the 0.8. Hit on his 3rd attempt, it's the 0.2 to the power of 2, 1 below this number, times by the 0.8. 4th attempt, it's the 0.2 to the power of 1 minus 4, times by 0.8. If you work these out, that one's 0.8, that one's 0.16, that one's 0.032, this one is 0.0064, and if you add those up, you get 0.9984. There's an over 99% chance that he will have hit before he gets hit for the first time, before he gets to the fifth attempt rather. The next question I want to look at, we're still basing it on the same archer, so we've still got a p-value of 0.8, but what if we want to know the probability he hits for the first time on his fifth throw or after his fifth throw? That will be x being greater than or equal to 5. His first success is on go number 5 or beyond number 5. Well, that means it could be on the fifth throw, or the sixth throw, or the seventh throw, or the eighth throw. Actually, there's no upper limit. It could, in theory, go on forever. So, let's look at what these probabilities are and see if we can spot a pattern. On the fifth throw, it's going to be 1 minus p to the power of 4 times by p. Here, it's going to be 1 minus p to the power of 5 times by p. Here, 1 minus p to the power of 6 and 1 minus p to the power of 7, and then still times by here. That is still using this formula each time. 1 minus p to the r minus 1 times by p. Now, as I said, this could go on forever, and really what we've got here is we need to work out that answer, that one, and all the other ones forever, up to infinity, and add them all up. If you get something like this, it's called a sum to infinity. A big S, a little infinity down there is the notation we use. And there's a formula which helps us do this. The formula is A over 1 minus R. This turns up in core maths. It's called a geometric progression and a sum to infinity. That A stands for the first number in your adding up list, and R is called the common ratio. What that is, it's what you're timesing your first number by to get the second number, and what you're timesing your second number by to get the third number. So if we have a look at our list here, the first number in our list that we have to add up, because we have to add up all of these probabilities, first number we have to add up is the answer to that. So that is A. And if you want to, you could just leave it as a sum, or you could work it out on a calculator. 0.2 to the power of 4 times by 0.8, it is 0.00128. Now, to get from this value to this value, and from this value to this value, and from this value to this value, this part of the sum is staying the same each time. What's happening is the 0.2, the power on it, is going up by 1 each time. That means to get from there to there, I'm timesing by 0.2. Because here this had 4 0.2s times together, this has 5 0.2s times together. To get from here to here, well, I had 5 0.2s times together, now I've got 6 0.2s times together. Again, I'm timesing by 0.2. And that works all the time. And that, what you're timesing by, that multiplier, that's called your common ratio. And that's denoted by R. So now I have this A value and this R value, I can put it in this formula and say the sum to infinity of this list is A over 1 minus R. A is 0.00128. 1 minus R, which is 0.2. And if I work that out on a calculator, I get 0.0016. So the probability his first attempt comes on the fifth throw or later than that is 0.016. I'm just going to write that answer down with what we have worked out, and next to that I'm just going to write out the answer we had earlier on, because earlier in this video we worked out the probability x is less than 5 to be 0.9984, and you should be thinking, well, less than 5 and greater than or equal to 5 covers absolutely everything. And if those probabilities cover everything, you should find that if you add them up, you get 1. And if you add those up, you do get 1. And that was just a little check we could make there on what we were doing.